Alright, very good morning to all of you. So I welcome you all on YouTube channel of Unacademy IIT JAM Live. This is your educator Srishti and I teach live on Unacademy's Plus platform in IIT JAM category. So today in this particular class what we are going to do, quick revision of molecular orbital diagrams of homonuclear diatomic molecules. Okay. So yes, let me wait for students to join this session. Then we are going to begin this class. Okay. Very good morning to all of you. Those who have joined this session, just let me know in the comment section if my voice is audible and you can see the screen. Okay. Just let me know once. Then we'll be starting off with our session. All right. Very good morning to all of you. Good morning, Sureka. Good morning, Sambhav. So this is going to be a quick revision of molecular orbital diagrams. Okay. So we are going to do quick revision of molecular orbital diagrams with the help of practice problems. Okay. So now we are going to start with our question. So let's take very first question in front of our screen, and this is your first question. Okay. So what you have to do in this question, arrange the following molecules in order of increasing fundamental vibrational frequencies. Okay, so these are four options given for this question. You need to arrange the molecules in increasing order of their fundamental frequency. Okay, so this is the first question. Just let me know your answers in the comment section. Good morning, Mosmi. Good morning, Ruby. Yes, so this is the first question. We have few questions for today's session, and we are going to do quick revision of homodiatomic molecular orbital diagrams of these molecules. Okay, yeah. So again, I'm repeating the question. You need to find out the correct order of fundamental vibrational frequencies, and you need to find out increasing order. Okay. Just make sure you all are clear with this term. Okay, that you need to find out increasing order. Yes, so what's your answer for this question, all of you? Just let me know your answers. I think this much time is enough for this question. Okay, just let me know your answers. Which is the correct order of increasing fundamental vibrational frequencies? Okay, all right. So B and A. Okay, what about others? What about Sambhav? What about Sureka? What's your answer for this question, Ruby? Okay. All right. See, the concept in this question is which concept we have to apply over here. The question is arrange the following molecules in order of increasing fundamental vibrational frequencies. Okay. Now, first of all, what is vibrational frequency? This is the formula of vibrational frequency. Mu is equals to 1 by 2 pi, okay, k by mu. This is the formula of vibrational frequency, okay. Mu is equals to 1 by 2 pi k by mu, where this 2 pi is constant. This is your force constant, all right, and this mu is your reduced mass. Okay, this mu is your reduced mass. So what you need to do, see the concept which we need to apply over here, we need to find out the bond strength, okay, or we need to find out the bond strength or force constant. Okay, if bond strength is higher for these molecules, that means fundamental frequencies will also be higher. Okay, so bond order or bond strength is directly proportional to fundamental frequency. Okay, so how we are going to calculate the bond order or bond strength? See, we need to take help of molecular orbital diagrams. Okay, so if I draw molecular orbital diagram of oxygen molecule, so I'm only going with valence orbitals, okay, not 1s and 2s, because anyhow these are going to cancel out their characters. Okay, so now we have 3 p orbitals for this oxygen and 3 p orbitals for this oxygen. Okay, so we don't have sp mixing in O2 molecule. Okay, so how this molecular orbital diagram would look like? So this is how you're going to form this molecular orbital diagram. There is no sp mixing over here. Fine, so this is your sigma and this is your sigma star. Okay, now 2 p orbitals, that means 2 pi orbitals, and here you are getting 2 pi orbitals. Okay, so this is how you should draw molecular orbital diagram for oxygen. Okay, what next we have to do? We need to fill up the electrons now. So this oxygen is having 4 electrons. Okay, and similarly we are going to have 4 electrons over here. Fine, so 4 and 4, 8. So 1 2 3 4 5 6 7 and 8. That means this is the molecular orbital diagram of O2 molecule. Okay, so if this is the molecular orbital diagram of O2 molecule, so what I can say over here, that bond order of O2, okay, bond order of O2, so this half character is cancelled out, this half character is cancelled out, so now you are left with one sigma bond and 2 pi bonds, which is from 1 electron. Okay, that means bond order is 2. I hope you all can understand this concept. Bond order is 2. Okay, so for O2 bond order is 2. Okay, what next we have to see? We have to see for O2 plus. Okay, and we have to see for O2 minus and O2 2 minus. Okay, so with increase in electrons and antibonding, you are reducing the bond order by 0.5. Now, if you remove one electron from antibonding, you are increasing the bond order by 0.5. Okay. Now, what we are doing when we are moving from O2 to O2 minus, we are adding one electron in antibonding. Now, if I'm adding one electron in antibonding, that means I'm reducing the bond order by 0.5. Okay. So, bond order will be 1.5 definitely. Then you are going to get 0.5 bond order. Find how we are going, how you are going to get, you are going to get one bond order. Okay, so it is reducing by 0.5. Okay, next you have O2 positive. So what you are doing, you are removing this anti-bonding electron, so that means the bond order is 2.5. Okay, so this is the bond order. So bond order, how you'll arrange this bond order in increasing way? So this is O2 minus, then you're going to get O2 minus, then O2, then O2 to positive. Okay, so this is your bond order. So can I say bond order is directly proportional to fundamental frequency? Can I say that, guys, bond order is directly proportional to fundamental frequency? Definitely it's directly proportional to fundamental frequency, right? So fundamental frequency order is going to be same. Okay, O2 2 minus, O2 minus, O2 and O2 positive. Okay, so this is going to be your correct order for fundamental frequencies. Okay, I hope this is clear to all of you, and the correct answer is option number A. Okay, the correct answer is option number A. Is it clear, Ruby? Is it clear? Okay, I hope Tarunesh and all of you are clear with this question. Okay, great. Let's take next question now, and this is your next question. Okay, what you need to do, you need to match the following. Okay, you need to match these options. So these are A, B, C, D, P, Q, R, S, T. Yes, this frequency is also stretching frequency. All right, Ashutosh, fundamental frequency is nothing but your stretching frequency. Okay. That's why the formula is like this. Okay. This is nothing but the formula of stretching frequency only. Fine. This one. Okay. And if you need to write down the stretching frequency in centimeter inverse, so you're going to add C over here. Fine. Okay. See, the best approach to solve this question is let's start solving this question. Okay, let's start solving this question. So, what we have to do over here, we have to draw molecular orbital diagrams of these four molecules. Okay, so let's start solving this question. Okay, B2, N2, O2 minus, and O2. So, how you're going to draw molecular orbital diagrams of B2, N2, O2 minus, and O2? See, we have B2, okay, then we have N2, we have O2 minus and O2. Okay, so these four molecules we have over here. What we need to do, we need to draw molecular orbital diagrams of these four okay, homodiatomic molecules. Fine. Yeah, I am waiting. Okay, you can solve this question. I am waiting. Okay, you can definitely solve it. No, it's O2 minus. Okay, Dhani, it's not O2 positive. It's O2 negative. Okay, this charge is negative. Okay. All right, guys. So yes, definitely. Right. Sorry for the delay. Actually, there is some technical issue. So now what we have to do over here, right? See, what we have to do in this particular question, we need to solve this question. We need to match these options. Okay. So what we need to do over here, first of all, we need to draw these molecules. Okay, how we are going to draw these molecules? See, we have B2, N2, O2 minus and O2. Okay, so these are options over here. So what we need to do, we need to draw molecular orbital diagrams. Okay, so what is the electronic configuration of boron? Electronic configuration of boron is 2s2 2p1. Okay, and electronic configuration for nitrogen is 2s2. Okay, it's 2p3. Fine, it's 2s2 and you have 2p4, and similarly 2s2 2p4. Okay, but in this case you have one extra electron, that means we have 5 electrons in p. Okay, so what we need to do in this particular case is, let's draw molecular orbital diagram. So you have 2p1. Okay, so you have 2p1, that means there is no there is sp mixing in boron. So this is how this molecular orbital diagram will look like. Okay, you have sp mixing, so definitely this is how this molecular orbital diagram will look like. You are going to get 2 pi orbitals first. Okay, like this. Okay, then you are going to get like this. Okay, then what next you have to do, this is 2 pi orbitals and this is 1 orbital. Okay, so this is how molecular orbital diagrams would look like for your boron. Okay, next you have nitrogen, again you have sp mixing over here, so similarly you have to draw these molecular orbitals like this. Okay, next you have oxygen, so there is no sp mixing, so like this. Okay, and there is no sp mixing, so like this you have to draw these molecular orbitals. Okay, what next we have to do over here, we need to fill these electrons. Okay, so we have 2 electrons in p, that means 1 and 2. Okay, we have 2 electrons, that is 1 and 2. Is it not visible? Is it not visible? Okay, should I increase the font? So that means you need you have 2 electrons and you have 3 electrons, so that means 3 from here, 3 from here, 6. Okay, so 1 2 3 4 5 6. Okay, what next you have, 8 electrons. Okay, you have 4 from oxygen, 4 from oxygen, but this time you have 10 electrons. Okay, so 1 2 3 4 5 6 7 8 9 10. Okay, this is how you have these electrons. Okay, this is O2 minus, not O2 2 minus, so you have 9 electrons. Okay, you have 9 electrons, so that's how you're going to fill it. Okay, next what you need to do, you need to take 8 electrons. Okay, so 1 2 3 4 5 6 7 8. Okay, this is how we are going to fill it. So what's the question? We need to find out the magnetism. So can I say, all right, so can I say this one is paramagnetic? Can I say boron is paramagnetic? Yes or no? Can I say that boron is paramagnetic? Is this point clear to all of you? Okay, so definitely boron is paramagnetic. So what I'm going to write down, I'm going to write down A over here. Definitely boron is your paramagnetic. Okay, next is nitrogen. Nitrogen is paramagnetic or diamagnetic? Nitrogen is diamagnetic. Okay, so next is your O2 2 minus. O2 minus is definitely paramagnetic. Okay, so what you are going to write down, you are going to write down C over here. Fine, next is your O2, it's also paramagnetic, that means you need to write down D over here. Fine, you need to write down D over here, right? Next is undergoes oxidation, that means it is losing its electron. Okay, so which compound will lose its electron? It's very obvious. Now if you have this electrons in anti-bonding, okay, so definitely that molecule will go oxidation. Okay, very simple concept. If you have electrons in anti-bonding, that means that molecule will go oxidation. Okay, so O2 minus will go oxidation and O2 2 minus will go oxidation. Okay, so these two compounds can go oxidation. So according to the question you have to solve. Okay, so what you can write down, you can write down C over here and you can write down D over here, right? Yes, more than one option is correct. Okay, more than one option is correct. According to the options given in question, you need to solve it. Okay, so O2 minus can go oxidation and O2 also can go oxidation. Okay, next is reduction. Reductions mean acceptance of electron. Okay, see, this boron can accept electron. Okay, this boron, one second. Okay, this boron can also accept electron because it is having vacant orbital, vacant bonding molecular orbital, so definitely Boron can accept electrons, so you need to write down A over here. Fine. Next is bond order greater than 2. Okay, next is bond order greater than 2 or equals to 2. Okay, we know bond order of O2 is 2. Okay, what next we have to see? Bond order of nitrogen is 3. Okay, so we can write B over here. Fine. So that's how we can write D and B option over here. Fine. Next is mixing of sp orbitals. So in case of boron, okay, you have mixing of sp orbital. In case of nitrogen, you have mixing of b orbital. Okay, sp orbital. So that's how you're going to solve this particular question. Is this question clear to all of you? Just let me know, all of you, is this question clear? I hope this question is clear to you. Is it clear? Just let me know, all of you. Sambhav, okay, Mosmi, Ashutosh, Akash, is it clear? Dhani, all of you, Sureka, Ruby. I hope this question is clear, okay? Great. So that's how you're going to solve this question, and according to the options given, you can go with the options, okay? So that's how you're going to solve it, okay? Great. So let's take next question, and this question is the next, okay? Assuming 2s2p mixing is not operative, which one is paramagnetic, okay? So if 2s2p mixing is not there, so which molecule is paramagnetic, that you need to find out, okay? Okay, so most of you are going with option number C. What about others? Okay, so 5 of you have given the answers. What about rest 5? There are 10 aspirants online, so you can definitely give your answers for this question. Okay, what is the question? If sp mixing is not operative, which one is paramagnetic? Simple concept, okay? Just you need to learn the molecular orbital diagrams. If you are clear with molecular orbital diagrams, you can solve these questions, okay? Great. So correct answer is definitely C. See, the short trick to solve this question is, we know this concept that Be2 doesn't exist. Okay. We know this concept that this doesn't exist. Okay. So we can directly cancel out this particular option. Okay. Now we are left with B2, C2 and N2. And we know we have 6 electrons in bonding in nitrogen. That's how we are getting 3 bond order. Okay. So if there is 6 electrons, so if you definitely, okay, one second, okay, I'll definitely tell you, Ashutosh, regarding your doubt. Okay, let me first complete the question. So basically, what's the case? If you have N2, right, and we have 6 electrons in N2, if there is sp mixing, okay, so that means we have 6 electrons. If there is no sp mixing, then only all orbitals will be filled. Okay, if all orbitals are filled, so that means this compound is not paramagnetic, this is diamagnetic. Okay, so this is not existing, this is diamagnetic. Now you have boron and carbon. Okay, so you have 2 unpaired electrons in boron if sp mixing is operative. Okay, so if sp mixing is not operative, that means in place of this pi you're going to get sigma. Okay, and you're going to pair these electrons, so this will become diamagnetic. Okay, this will become diamagnetic. I hope you are understanding this particular question. Okay, it's very, very important. Fine. Next you have carbon. So what next you have to see? You have 4 electrons. Okay, and definitely there is sp mixing. So that's how you can see this concept. Okay, it's diamagnetic. Okay, if sp mixing is operative, it's diamagnetic. But if I just remove this sp mixing, so that's how these orbitals will look like. And you need to fill 4 electrons. Okay, so 1, 2, 3, and 4. Right, so that means this compound is paramagnetic. Okay, this compound is paramagnetic. So option C is definitely your correct answer, that is C2. Okay, I hope everything is clear. There is no need to draw full molecular orbital diagrams, because now you have to actually solve like this. Okay, there is no need to waste your time. Fine. Okay, great. So let's take next question. So, which test series is not visible? The previous test series or the live test series? Just let me know once, okay? Which is not visible to you? Live test series or previous? Previous classes is not visible. Previous test series or live? Oh, so okay, previous ones, okay? So I'll definitely check it, okay? I'll check it. So today you have one more test series. Okay, you have one more test at 2 p.m. So that's why we don't have any practice session today. So after this class, okay, you can take some rest and you can just give your examinations, because that's also important, because we need to develop that state of mind. So tomorrow we are going to take chemical equilibrium practice session. Okay, great. So this is the next question. You can read this question, and it's MSQ. Okay, it's not MCQ, it's MSQ. Okay, it's not visible. The question is, the color of X2 molecules of group 17 elements changes gradually. Yes, it's MSQ. Okay. So the question is, the color of X2 molecules of group 17 elements changes gradually from yellow to violet down the group. Okay. This is due to, options are, option A, the physical state of X2 at room temperature changes from gas to solid down the group. B option is decrease in homo-lumo gap between down the group. C option is decrease in pi star sigma star down the group. Decrease in ionization energy down the group. Okay, so this is your question. Okay, see, the concept is the color of X2. Okay, what's the question? The color of X2. So this X2 can be your fluorine. Okay, it can be chlorine, it can be bromine, or iodine. Okay, so these are 4 compounds: fluorine, chlorine, bromine, and iodine. So now you tell me, sp mixing is present in fluorine or not? Do we have sp mixing in fluorine? Yes or no? Okay, sp mixing is present in fluorine. Yes, so there is no sp mixing in fluorine. Okay, there is no sp mixing in fluorine. Fine, so sp mixing is absent in fluorine. Fine, but sp mixing is actually present in case of chlorine, bromine, and iodine. Okay, so sp mixing is definitely present. Fine, what next we have to see over here? The question is, the physical state of X2 at room temperature changes from gas to solid down the group. Okay, so now if I go from fluorine, okay, chlorine, bromine, and iodine. Okay, so just tell me, what is the physical state of fluorine at room temperature? What's the physical state of fluorine at room temperature? It's gaseous in nature, definitely. Can I say that? Fluorine is gaseous in nature. Okay. Next you have chlorine. Fine. It's also gaseous in nature. Great. What about bromine? Bromine is liquid. Can I say that bromine is liquid at room temperature? Okay. And iodine is solid at room temperature. Okay, iodine is solid at room temperature. So fluorine, chlorine, bromine and iodine. Okay, so definitely iodine is solid at room temperature. Okay, so now what's the question? The question is the physical state of X2 at room temperature changes from gas to solid down the group. So can I say this statement is correct? Can I say this statement is correct? Option number A. Any doubts to anyone? Right? Yes, definitely it's violet crystals. Any doubts to anyone? Can I say this statement is absolutely correct? The physical state of X2 at room temperature changes from solid, gas to solid down the group. Okay, so yes, definitely this statement is correct. Okay, next is decrease in HOMO-LUMO gap, and this statement is also correct. Now, what is your HOMO or LUMO? Let's suppose I draw a molecule of this. Okay, let's take this thing that I am just writing down the molecule of your chlorine. Okay, so in case of chlorine there is no sp mixing, so that's how these molecular orbital there is sp mixing. Okay, so that's how these molecular orbital diagrams will look like. Okay, you're going to get like this orbitals. Okay, then you are going to get like this. Okay, and you'll be having sp mixing, so that means you are going to have two p orbitals, then one sigma, then two pi orbitals, then one sigma. Okay, so that's how you're going to get molecular orbital diagram. Okay, for sp mixing. Now what next we have to see over here? Color does not depend on physical state. See, the concept is the physical state of X2 at room temperature changes from gas to solid down the group. Okay, we are talking about physical state, so option number A is correct. Okay, but yes, color doesn't depend on the physical state, it depends upon electronic transition. Okay, which lies in your visible region. Fine, so that's the reason for this concept. But yes, the question is the physical state of X2 at room temperature is from gas to solid. It's actually changing from gaseous state to solid state. Okay, so option number A is absolutely correct. Fine. What next we have to see? We need to see the HOMO-LUMO gap. So if I have 5 electrons in this chlorine, so that means I need to fill 10 electrons. Okay, so 1 2 3 4. Okay, yeah, see the physical state. Okay, the physical state of X2 at room temperature changes from gas to solid down the group. Okay, yes, it's the result. See, the option is the physical state of X2 at room temperature changes from gaseous to solid down the group. So there is no information on color in this particular statement. Okay, there is no information on color on this particular statement. Just you need to find out the correct answer. Okay, and you know this thing that from fluorine, chlorine, bromine, iodine, the physical state is changing from gaseous state to solid state. That's the reason for option number A. Okay, I hope you are asking this question only. If you are asking something else, okay, please write down your question correctly. Okay, so now what I can see over here, this there is no sp mixing, but the concept is this HOMO-LUMO gap is actually decreasing. Okay, this HOMO-LUMO gap is actually decreasing. Okay, so the question is the color of X2 molecule of group 17 elements changes gradually from yellow to violet down the group. Okay, all right, fine, so that's my mistake. Okay, yeah, it's on me. So yeah, it's on me. The question is yes, definitely. Okay, so yeah, it's on me. Okay, I take this question on me, but basically it's my mistake. The question is, what is the question? The color of X2 molecules of group 17 elements changes gradually from yellow to violet down the group. This is due to. Okay, so you need to tell the reason. Right, correct. Okay, so yes, definitely this is not the reason. Okay, so I thought that we need to find out the correct statements. Okay, yes, definitely this is not the reason. The reason is not this physical state. Okay, yes, definitely the reason is not physical state. Okay, so it's on me. I'm really sorry for this confusion. So this is incorrect option. Okay, this is incorrect option. Fine. What next we have to see? Decrease in HOMO-LUMO gap between a gap down the group. So yes, definitely this is the reason. Okay, so due to decrease in HOMO-LUMO gap, what's your HOMO? Okay, so can I say pi star is your HOMO? Can I say that pi star is your HOMO and sigma star is LUMO? Yes or no? Can I say that pi star is HOMO and sigma star is LUMO? Right, can I say that pi star is HOMO and sigma star is LUMO? So what is the concept? Okay, the gap, the gap of the energy gap between HOMO and LUMO is actually decreasing from moving from fluorine to your iodine. Okay, so definitely this is the reason, and decrease in pi star and sigma star down the group, same concept. Okay, so yes, it's the reason. Decrease in ionization energy down the group, this is not any reason for color. Okay, this is not any reason for color. So correct answer is definitely B and C. Correct answer is definitely B and C. Okay, yeah, B and C are the same options. Fine. All right, so let's take next question. I hope you are clear with the confusion. Okay, so that's my mistake. Actually, I thought we need to find out the correct options. Okay, so the question is we need to find out the reason for the color. Okay, so yes, physical state is not a reason for color. Okay, great. So let's take next question, and this is your next question. Yes, so the concept is, see what we need to think over here. See, the concept is, if I talk for fluorine, okay, chlorine, bromine, and iodine. Okay, so can I say if I'm going from left to right, so energy gap is decreasing? Can I say that, guys? Energy gap between HOMO and LUMO is decreasing. Can I say that energy gap is decreasing, right, from your fluorine to iodine between your HOMO and LUMO? So definitely energy gap is decreasing. Okay, yeah, so we are not discussing any question, just I'm telling you the concept of the color. Okay, so energy gap is actually decreasing between your HOMO and LUMO. Okay, so if this is the case, all right, if this is the case, so if energy gap is decreasing, what is energy? Energy is equals to EHC by lambda. Okay, if energy is decreasing, can I say wavelength should increase? Yes or no? Can I say that wavelength should increase if energy is decreasing? Okay, one concept. So basically, if your energy is less, okay, if your energy is less, that means you need light of high wavelength, right, for electronic transition. Okay, yes, I am telling you, Sonia. Okay, just listen to it first, listen to it. I am telling you the reason. Okay, just at least give me 1 minute. I am telling you the reason. Okay, the concept is energy is decreasing and lambda is increasing. Okay, so energy is decreasing and lambda is increasing, that means you need light of high wavelength. Okay, so now if I draw Vibgyor, okay, if I draw these colors Vibgyor, so from moving from this violet to red, okay, wavelength is increasing. Can I say that wavelength is increasing? Yes or no? Can I say that wavelength is definitely increasing? Okay, so if wavelength is increasing, that means energy is less and wavelength is increasing. Okay, so have you heard this term complementary color theory? Yes or no? Have you heard this term complementary color theory? Okay, so basically if you have less energy, okay, so it will absorb high wavelength value. Okay, but it will actually give you, okay, less wavelength value in visible region. Okay, so that's the concept over here. If it's absorbing high wavelength energy values, it will show you less wavelength energy values. Okay, that's why this iodine is violet in color. Okay, and this bromine is light brown something. Okay, this one is your pale yellow, fine, and this is your colorless. Okay, or very pale yellow color is there. Okay, so that's the reason energy is less, high wavelength, but it's actually showing complementary colors. Okay, great, fine. So let's take next question now. Okay, I hope you are clear. Is there sp mixing in nitrosyl? Okay, so we haven't discussed these questions in our plus courses. Okay, so we'll be starting off with this topic only in the next class. Okay, so after that you will be clear with this question. Yes, that you need to find out. Okay, whether it's your MSQ or MCQ. Okay, just read the questions, find out the correct answer. Okay, if you're getting more than one option correct, then definitely it's MSQ, otherwise you can go with MCQ. Okay, so let's start discussing this question. So what's the question? We need to find out the correct statements. Okay, so definitely we have sp mixing in case of C2. So that's how we are going to draw these molecular orbital diagrams. Okay, we have sp mixing. So we have two electrons, four electrons. That means that's your molecular orbital diagram for C2. Now we are adding two more electrons. Okay, and this time what we are doing, we are adding two more electrons in this particular bonding molecular orbital. Okay, so that's how we are going to add two electrons over here. So what you can see, yes, definitely it's diamagnetic, because there is no unpaired electron. Okay, so yes, it's diamagnetic. Option number A is absolutely correct. Okay, next statement is O2 2 positive has a longer bond length than O2. See, now the question is very easy. Okay, see, you have O2 and O2 2 positive. Okay, so you have electrons and anti-bonding in O2. Okay, now you have removed these electrons from anti-bonding. So what will happen? Now if you are removing electrons from anti-bonding, that means you are increasing bond order. If you are increasing bond order, so which results in decreasing bond length. Okay, so that means if I write down the order for bond length, so bond length, okay, if I'll write down order, bond length of O2 is greater than O2 2 positive. Okay, so O2 2 positive has a longer bond length than O2. This statement is incorrect. Is it clear? I hope you're getting the point. This statement is incorrect. O2 2 positive has a shorter bond length. Okay, it's not having the long bond length. Okay, because the bond order is high, so it's inversely proportional. Bond length and bond order is inversely proportional to each other. Okay. Next concept is N2 plus and N2 minus have same bond order. So what's the concept? See, this is how we can draw the molecule. Okay, we have N2 like this. Okay, so N2. Now what we are doing, we are removing one electron. Okay, so definitely the bond order will be reduced by 0.5. Okay, now we are adding one electron in antibonding, definitely bond order will be increased by 0.5. Okay, so now that's why I have put more emphasis on your theory portion. Now I think you are clear with the theory, so there is no need to write down the molecular orbital diagrams. Okay, we can just directly solve this question. Fine. So option number C is absolutely correct. Okay, option C is correct. He2 positive has same energy as two isolated helium atoms. Now you have helium. Okay, that means 1s2. Fine, you have helium 1s2. Okay, so you have four electrons like this. Okay, helium 2 positive, that means you have only one electron in anti-bonding. Now if you have one electron in anti-bonding and you have isolated helium atoms, that means this is the level of orbitals. Okay, now you have electron in this orbital in He2 plus, and you have electron in this orbital in helium. That means your atomic orbital. This is your atomic, this is your molecular orbital. So what's the concept? Okay, see, has same energy, definitely there is difference in energy, right? Helium will be lesser in energy. Okay, helium orbital will be lesser in energy in He2 plus. Okay, so if I take the ionization concept, so ionization energy of helium is greater than your helium 2 positive. Am I clear? Ionization energy of helium is greater than your helium 2 positive. Okay, because from in helium you have to take electron from atomic orbital, and in He2 plus you have to take electron from anti-bonding atomic or molecular orbital. Okay, and this process is easy. Okay, you need less energy to take off the electron. Okay, great. So let's take next question now. I hope you are clear with this question. This is your next question. Okay, great. Okay, good job, Madiha. Very fast. Okay, great. Let's see if you have answered it correctly. What about others? Okay, so most of you are going with option number B only. I think all of you, right? So let's start solving this question. The question is, which among the following are correct statements? Okay, so you need to identify the correct statement. So option number A is order of oxygen bond length is in this order. Okay, see what we can understand from this concept is what is this complex. Okay, can I say oxygen is present in O2 positive form? Can I say that oxygen is present in O2 positive? So basically they are asking this order: O2 positive, O2 and O2. This one is negative, right? So positive O2 and O2 negative. Fine. So what we need to do, we need to find out the correct order of bond length. Okay, bond length. See, the concept is very clear. Okay, you have two unpaired electrons in anti-bonding of oxygen in molecular orbital diagrams. Okay, now if you are adding one electron, that means you are adding one electron in anti-bonding, so bond order is going to decrease and bond length is going to increase. Okay, so yes, this order is correct. Now let's compare these two species. Okay, so now if you are removing one electron from anti-bonding. Okay, now if you are removing one electron from anti-bonding, so you are increasing the bond order and you are decreasing the bond length. Okay, so yes, this order is definitely correct: O2 positive, O2 and O2 negative. Okay, great. So that means option A is absolutely correct. Option A is absolutely correct. Let's take next option. Though ethyl alcohol and dimethyl ether have same molecular weights, dimethyl ether is more volatile than ethyl alcohol. Okay, dimethyl ether. Fine, they are asking for dimethyl ether and ethyl alcohol. Okay, so now you guys tell me, right? It's given in the question that dimethyl ether is more volatile than ethyl alcohol. So what's the reason for this concept? Okay, although this is very elementary question, very basic one, but still, what's the reason for this question, this concept, that why dimethyl ether is more volatile than ethyl alcohol? If you think this option is correct, then only you justify this question option. Okay, just please justify this option. Why dimethyl ether is more volatile than ethyl alcohol? Yes. So basically we have significant amount of electronegativity difference. So basically we can have hydrogen bonding in case of ethyl alcohol. Okay. So due to hydrogen bonding, this is less volatile than your dimethyl ether. Okay. Irrespective of having same molecular weights. Okay. So option number B is also correct. Okay. Option number B is definitely correct. Now let's take next option, that is third. Okay. Yeah. So third option is the order of bond order is this one. Okay. The order of bond order. Definitely this is the correct bond order. Why? Because this is how we fill electrons in N2. Okay. This is how we fill electrons in N2. Now if I take electron from N2, that means I am taking electron from bonding molecular orbital. So order will be reduced by 0.5. Okay. Then in this case we are adding two electrons. That means what we are doing, we are reducing bond order. So definitely this is the correct bond order. Now if I need to calculate the bond order, so we know this concept that bond order for nitrogen is 3. Now we are taking off one electron from bonding molecular orbital. So what will happen? It will be reduced by 0.5. Okay, so it will be reduced by 0.5. Now we are adding electrons to anti-bonding. We are adding 2 electrons. Okay, so it will be reduced by 1. Okay, so that means bond order will be 2. Okay, I hope you all are clear with this concept. Any doubts to anyone? So bond order will be 2. Okay, so this is the order of your correct, this is the correct order of your bond order. Okay, so option number third is also correct. Okay, next is ice has more density than water. Very important application. Okay, you can observe this thing in day-to-day life also, but yes, it has very significant role in phase equilibria. Okay, so basically ice is lesser denser than your water. Okay, so water is having high density. If I compare density, so water is having high density in comparison with your ice. Okay, right? If I just go with the concept, then solid must be having high density, but specifically for water and some other solvents, this is the case. Okay, so correct answer is option number B. Okay, correct answer is option number B. I hope you are clear with this explanation. Okay, so correct one is option number B. Great. So this is our next question. Okay. Okay, one more addition to this question. One more addition. You need to tell character of Lumo also. First option, first question. Second question is you need to tell character of Homo also. Okay, you need to tell character of Lumo also, and you need to tell character of Homo also. Okay, so the question is the character of LUMO of N2 and O2 minus, O2 2 minus. Okay, this is your nitrogen and this is O2 2 minus. You need to tell character of LUMO of N2 and O2 2 minus. Okay, you need to find out basically the symmetry of your this LUMO of N2, and second part is you need to find out symmetry of HOMO. You should not take more than 30 seconds for this question. Okay, see the concept over here is what we need to do. We need to find out the character of LUMO and HOMO. Okay, so let's start with N2. Okay, so this is how we can draw excuse me, molecular orbital diagrams of N2 like this. Okay, there is sp mixing, so that's how we are going to draw it. Okay, so you have 6 electrons over here like this. Okay, so what can I say that this is your HOMO. Okay, and this is your going to be LUMO. Fine. So what we need to do, we need to find out the character for HOMO. So this bond is nothing but sigma bond. Okay, so what we need to do, this is sigma, and we need to find out symmetry notation for sigma. Okay, so how this orbital will look like, this is p orbital. Okay, so that means this is how you can draw sigma orbital. Okay, this is how you can draw sigma orbital. Okay, positive, positive, one nucleus. Okay, that's how we can draw sigma orbital. Can I say that, guys? Okay, that's how we can draw sigma orbital. This is your sigma orbital. Now what we can observe over here, that definitely there is symmetry element. Okay, this is symmetrical in nature. Okay, if we just go in this direction, okay, so definitely this one is symmetrical in nature, so I can give G notation to this particular HOMO. Okay, I can give G notation to this particular HOMO. Is this point clear to all of you? Any doubts to anyone? So this is the notation for HOMO of N2, okay? But in the question we need to find out the LUMO notation, okay? So LUMO is this orbital, that is pi star, okay? So it's pi star, first of all it's pi star, okay? So how we can draw this molecular orbital diagram for pi? See, it's pi star, okay? So we can draw molecular orbital diagram of pi star like this. Yes or no? This is how we can draw the molecular orbital of pi star. Just let me know. This is how we can draw molecular orbital, a diagram of pi star, okay? And there is definitely symmetry, okay? There is definitely symmetry. So it's pi g. Okay, it's pi g. That means LUMO of N2 is pi g. Okay, LUMO of N2 is pi g. What next we need to do? We need to find out for O2 2 minus. Okay, what we need to do? We need to find out for O2 2 minus. Okay, so let's do that for O2 2 minus. So O2 2 minus means this is how it will look like. Okay, pi star and 1 2 3 4. Okay, O2 2 minus 1 2 3 4. So this is going to be your HOMO and this is your going to be LUMO. So if I talk for HOMO, this is pi star, and just now we saw that this is pi g. Okay, so pi g, and for LUMO of O2 minus, this one is sigma star. Okay, so sigma and sigma star is your ungenerated. Okay, because this is how we should draw sigma star. Okay, like this. You have one nucleus, positive and negative. Okay, so if you see, there is no center of symmetry, or if you rotate this molecule, there is no this positive sign is replacing your negative sign. Okay, so this is sigma u. So correct answer is option number B. Okay, so HOMO is this, LUMO is this, HOMO is this, and LUMO is this. Okay, I hope all of you are clear with this question. Okay, just in case you have doubts in this question, you can definitely ask. Okay, so yeah, let's take next question. This one is very simple. Okay, time and again you will see these questions coming in your examination. Okay, if you just see the previous year question, if you just see the questions from previous year, so you'll see a lot of questions. Just okay, it's nothing but a repetition. Okay, sometimes they ask you bond order, sometimes they ask you bond length, sometimes they ask you thermodynamic stability, sometimes they ask you bond strength, okay, frequency, all these factors. I think you should give the answer in 5 seconds, okay? I'm expecting your answer in 5 seconds. Yes, definitely. Okay. So the correct answer is option number D. I don't think that we need to explain this question again and again. Okay. So the correct answer is option C. This is your bond order. Okay. So bond order is like 2.5. Then it's like okay, 1.5. Then it's like 1. Okay. So this is how you can write down the bond order. Okay. Let's take next question. Yeah, I think this is the last question, right? This is the last question for this session. So this is the last question, and what you need to do, you need to find out the correct option. Okay, and the question is, which of the following statements are correct? First is, amongst these five species of oxygen, which one has the greatest thermal stability? Okay, second one is, double bond in C2 exists of both pi bonds because of the presence of 4 electrons in 2 pi molecular orbitals. Okay, third one is, amongst B2, C2, N2 and O2, mixing of 2s 2p orbitals takes place only in nitrogen molecules. You need to find out the correct option. I'm writing fourth option also. Okay. Yeah, there is no fourth option, so you just ignore this fourth option. Okay, there is no fourth option. Great, great. So definitely the correct answer is option number A. How the correct answer is option number A? See, this is the only positive species. Okay, that means the bond order should be maximum for this particular species in case of oxygen. Okay, I'm not talking in general. That depends on your molecular orbital diagram. But right now, in case of oxygen, this should be your order. Okay, if this is your order, so what you can understand over here, that definitely it's going to have highest thermal stability. Okay, it's going to have greatest thermal stability. So option number A is absolutely correct. Okay, double bond in C2 consists of two pi bonds because of the presence of 4 electrons and 2 pi atomic orbitals. Yes, it's also correct. Okay, you have two atomic orbitals, like you have two molecular orbitals and you have 4 electrons in these two molecular orbitals. So option number second is correct. Okay, amongst B2, C2, N2 and O2, 2s2p mixing orbital takes place only in N2 molecule. That's incorrect option, because in this case also you have 2s2p mixing, in this case also, and in this case. Okay, so option number A is definitely correct. Okay, I hope this is clear to all of you. Fine. So yeah, I now you guys have exam at 2 p.m. Okay, you have championship test, so you just take some rest and prepare for that. Okay, and now we have practice session on chemical equilibrium on November 9th. Okay, that means tomorrow 12 p.m. Okay, 12 p.m. The timings are same, but this class is going to be tomorrow. Okay, so those of you who are present this session in this session and you want to attend this class, it's a free live class. Okay, so you can attend it tomorrow. The timing is 12 p.m. Okay, yeah, I'll share it. Okay, I'll share it, Sambhav. I'll share the PDF. Okay, so the timing is 12 p.m. tomorrow. And if you want to attend revision courses on which is ongoing on Plus platform. Okay, so right now which all courses I'm taking revision of inorganic chemistry. Okay, in these two batches I'm taking revision of inorganic chemistry, so you can also join live for these classes. Okay, and there is one more ongoing course which is very beneficial for you guys, that is practice course in jam chemistry. Okay, so we'll be doing crash course of chemistry for your IIT JAM 2021 with the help of practice problems. Okay, so if you need to attend live classes for these courses, this is my referral code. Okay, you can use it for 10% discount. Okay, SBATRA, this is my referral code. Okay, just in case you have some queries. Okay, so you can drop a message on Unacademy my profile, for which you can find the link in the description box, or you can find the Telegram channel link also. You can join that Telegram channel. Okay, so any more doubts? Okay, see YouTube timings. Okay, see the concept is YouTube timings are 10 a.m. only. Fine, so we'll be taking questions, we'll be taking YouTube classes on Sundays. Okay, basically I'm going to take YouTube classes on Sundays. Okay, or sometimes Tuesdays or Fridays. Okay, so any 2 days, right? I'll be taking classes on any 2 days. Okay, always we will be having one class on Sunday. Okay, then we have to decide between Tuesday and Friday. Okay, so for that I'll be sharing the links in groups. Okay, so you can join the Telegram channel. Okay, great. So timings will be only 10 a.m. Fine. Okay, so what's your doubts, Sonia? Is O2 2 minus is highest thermal stable as it has pair electrons? No, no. See, the thermal stability lies from, that is your thermodynamic stability. Okay, so whenever you have electrons and antibonding, that's not thermal stable. Okay, in O2 2 minus you have electrons and antibonding. Okay, O2 2 positive is more stable. Okay, see, if you have electrons and antibonding, that means it's not thermodynamically stable. Okay, in comparison, I'm saying. Okay, so you always have to see electrons in bonding molecular orbital. Is it clear, Sonia? Is it clear? I think your doubt is clear. Okay, so I'll see you in the next class. Okay, that's tomorrow 12 p.m. and then we have next class at 8 p.m. Okay, so one is tomorrow 12 p.m. and one is 8 p.m. class. Tomorrow we are going to have two classes. Okay, 12 p.m. and 8 p.m. So one class is on special platform, that's a free live class. Okay, practice session on chemical equilibrium. Okay, and next class is at 8 p.m. potentiometric titrations. Okay, these two classes we have for tomorrow. Okay, I hope you are clear with the concepts. Okay, just revise the questions and we are going to take more such practice sessions on YouTube. Okay, so I'll see all of you in these two classes. Take care. Bye bye.